So let's talk about how we get a constant field. I already hand waved and said it comes from a sheet, a two-dimensional sheet of charge, right? So constant field, two-dimensional sheet of charge. So let's go ahead and calculate the electric field due to a sheet of charge. Now, a sheet of charge, I'm actually going to start, rather than with a square sheet, I'm going to start with a round sheet, like a disk of charge. So this is a two-dimensional disk of charge. This is a disk 2D. Okay. Let's say it's a conducting disk, so the charge can redistribute itself evenly. Or let's just say the charge is distributed evenly. The charge, total charge Q, I would just say there's a bunch of plus charges all over the disk. I'm not going to draw them all, but there's a bunch of plus charges all over the disk, evenly distributed, so that it has a constant charge density. Charge density, right? Charge density in 3 dimensions would be charge per unit volume, but this is 2-dimensional charge density, so it is charge per unit area. Actually, let me do an aside. Charge density. We are going to care about charge density. Charge density, right, in 3 dimensions is charge per unit volume, and that is rho density. In 2 dimensions, it's sigma, that's charge per unit area, and in 1 dimension, it's lambda, charge per unit length. So if you're talking about a sphere of charge, right, charge per unit volume. If you're talking about a disk of charge, charge per unit area. If you're talking about a line of charge, charge per unit length, charge density. We're going to care about charge density. That's going to help us to solve these problems. Okay, so we're at a disk. It's got a constant charge density, sigma, and we say sigma is charge per unit area. Well, what's the, oh, I forgot to give you the dimensions of the disk. Let's just say the disk has a radius of capital R, a fixed radius of capital R. So the charge density is Q over, whoops, not Q over R, over the area of the disk, Q over A, which is equal to Q over, what's the area of a disk? Pi R squared. Easier for us later to talk about the sigma charge density rather than the total Q charge Q. Okay, so we want to find the field above this disk. When I say above, right, the disk is sort of, it's just sitting out there in 3-dimensional space on one side of the disk or the other side of the disk. But let's actually put the disk, let's say in 2 dimensions, right, side view. Here's the side view of the disk. And just say, let's take the central axis and start at least just by talking about what is the field at point P, which is a distance d from the disk, from the center of the disk. So we're going to ask for what is the field there. Say, okay, all right, so we got to find the field. That's supposed to be a capital E. We got to find the field. And how do we find the field? Due to a collection of charges. You know this, right? We find the field due to a collection of charges by breaking the object up into little point charges and just saying, and this is, right, the disk is 2 dimensions, so they're both in and out of the page and up and down. But we break it up into a whole bunch of point charges. So look at the disk drawn in the 3-dimensional space, right? We just take a whole bunch of point charges and we find the field due to every single one of these little point charges and we add them up. Okay, so that's what we're going to do, but we're going to do it in a very systematic way. And instead of just taking arbitrary point charges, what we can do is break this disk up into rings. Look at the 2-dimensional or the 3-dimensional picture. I don't know if you want to call this a 2 or a 3-dimensional picture. But let's break the disk up into rings. And let's just take a ring at some arbitrary radius. Remember, the whole radius of the disk is capital R. But let's just take a ring at some arbitrary radius because we're going to have to look at all the rings that make up the disk. And let's call that little r. Whoops, that was a bad color because it's hard to see. I'm just going to draw a little r in red also. So little r is an arbitrary ring that makes up the disk. What I'm going to do is break up the disk into a lot of rings from the inside to the outside, actually an infinite number of rings, in order to make this an exact calculation. Each ring is at a radius little r, where the total disk has a radius big R. Let's just take one of those rings and just consider one of those rings. So I took out one of the rings from some arbitrary radius little r, and say, what is the field due to the ring at point P, which is a distance d from the center of that ring? You see now what we're going to do then, we're going to say, oh, we'll break the ring up into individual point charges, find the field due to each of those point charges at P, then we'll know the field of the ring, and then we can add up all the rings to find the field of the disk. So we're taking it sort of stepwise. So we're going to break the ring up into little point charges, and we'll say, what is the field due to each of these point charges? And then we'll add up all the rings. Once we found the field of a ring. But we've already found the field of a ring. We did this for gravitation. It's the exact same thing. Found the force of a ring of mass on a point mass at point P, and the field, remember, is just force per unit mass, or in this case, force per unit charge. So if we found the electric force of a ring of charge on a charge at point P, and then just divide out that charge, we get the field. But we found the force before, so we know what it looks like. But you should look back at when we found the force of a ring of mass and see that I'm just going to repeat the derivation, but I'm going to do it quickly because we've done it before. So we have to be careful with our notation here. If the disk has a total charge big Q, then the ring is going to be just a part of that. We're going to call it a charge dq. Each ring has a charge dq such that Q is the sum of all the dq's, of all the rings, sum of all the rings. But each ring dq is going to be broken up into point charges, which I guess we'll just call the point charge little dq, such that big dq equals the sum of all the little dq's. So when we add up all those point charges, we end up, for all the rings, and add up all the rings for all the disks, we end up getting big Q. Okay. In order to solve for the field of the ring, what we want to do is say, okay, so if we take a single point charge, let me make it a red. We're looking at this point charge. We know that that has a field at point P, which points in this direction, which has an angle of theta with, let's call this the x-axis. Let's call that the x-axis, just so we have something to refer to. It has an angle theta, and the field, due to the charge dq, the field due to just this little charge here is equal to, sorry, I got to write it over here. I'm going to call it dE is equal to k dq over the distance squared, but the distance is this distance here, which is the square root of r squared plus d squared, little r squared plus d squared. We've done this before. Then you find the field due to this one, which points in that direction, which has the same magnitude, but points at an angle theta above the plus x-axis. So you can see that when you add those two vectors, that the vertical components cancel, the y components cancel, and the x components add, and that's going to be true for every pair of points on the circle, so that all we care about for any of these dE's is the component in the x direction, which is the magnitude times the cosine of theta, where theta, or where cosine theta is, if this is theta, then this is theta, then the cosine of theta is adjacent, which is d, over hypotenuse, which was the square root of r squared plus d squared. Oops, oh dear, I forgot to square my distance here. That's a distance squared. kq over distance squared. This distance is r squared plus d squared. Okay, and field in general for a point charge is kq over r squared, where, that's our sort of arbitrary field of a point charge. Okay. So the problem here is we've got the ring is also a infinitesimally small slice of the disk, while the point charge is an infinitesimally small slice of the ring. So we've got a lot of infinitesimally small dE's, right? We've got the dE, which is the field due to the ring, and the dE, the dE, which is the field due to the point charge. But the field due to the ring is the sum of all the point charges that make up the ring. That's what this integral says. And again, exactly the same as when we did this for masses. So what you end up getting is the integral. We're integrating around the ring. I just didn't figure out what variable we're integrating yet. Integrating around the ring, k dq over the square root of r squared plus d squared times the cosine of theta, which is d over the square root of r squared plus d squared. And so if you look at this integral, everything is constant except for dq, our integration variable. Everything is constant. Little r is constant for the ring. D is constant, the distance from the ring. And k is constant. It is, by definition, a constant. So what you end up getting is the field of the ring is now this. We pulled out the constants, and I just neatened it up a little bit. And so all that's left is dq. We're integrating that around the ring. That is, therefore, just the total charge of the ring. So the total charge of the ring is capital dq. dq over r squared plus d squared to the 3/2. Okay, so that's the field due to the ring. And then we're adding rings from the smallest ring in the center to the biggest ring on the outside, and each of these rings has, a little bit of width, right? That's each ring. Okay. The electric field of the disk is the sum of all the electric fields of the rings, but now we're adding these rings from a radius of 0 to a radius of capital R, and that makes up for the whole disk. And so we have to do the integral from r equals 0 to r equals capital R of k d dq over r squared plus d squared to the 3/2. Now here's where the charge density comes in. This is an important point. What is constant here? What is constant is k is constant, d is constant. I didn't draw that in this picture on this page, but d is the distance from the disk. R is no longer constant. That's what's important. R is no longer constant because R is now one of the variables we're integrating over, yet the integral variable is Q. So we need to find a relationship between Q and R. This is the point behind all of we do these integrals in physics all the time. We did a couple last semester. It's always finding some kind of relationship between two variables which don't seem to have any relationship, like mass and distance. In this case, it's charge and distance. So we need to go back and look at a single ring. Sorry, I changed my color again. But let's just look at a single ring at a distance r. It's got a charge dq. So the ring actually has an area, right? Because we sort of said it but didn't make a big deal out of it, that it's infinitesimally skinny. So we can talk about its width as dr. So you really think about, let's look at it instead of in two dimensions. Instead of trying to look from the side of the ring. Here's a front view of the ring. We sort of say this is r, and this is the ring takes up the space from r to r plus dr. That's the size of the ring. It takes up a space from r to r plus dr. So the area of the ring, we can talk about the area of the ring, dA. It's a ring, right? It's not a disk. It's got a circumference of 2 pi r, and it's got a width of dr. That's the area, the circumference times the width. And therefore, here's the key. Here's what's important. I hesitated there because I wasn't sure therefore was the right thing. But anyway, the density of the ring, the charge density of the ring, is the same as the charge density of the disk, right? They have the same, because the charge is evenly distributed. That's the whole point of talking about charge density. So the charge density of the disk, which was Q over pi r squared, is equal to the charge density of the ring, which, remember, the ring's charge is dq, and the ring's area is dA, which is 2 pi r dr. So this is charge over area. This is sigma. So this is, and you might say, wow, how would I have ever known that? Well, the reason why you would have known that is because this is what we do every time we solve integrals like this. You just have to know that we always have to look at the relationship between two variables using density. It's always some kind of density. It's always some charge per unit area, charge per unit volume, charge per unit length, mass per unit area, mass per unit volume, mass per unit length. We use that, say, since the density is constant, the density for the smaller object must equal the density for the larger object. But this is what we end up getting. Charge per unit area for the disk is equal to charge per unit area for the ring. And that's what gives us a relationship between dq and r and what allows us to do this integral. I don't know what kind of animal this is, but let's solve for dq in terms of r inside the animal. I made one small error here before we go on to the next page, and that is that the tail end of our animal here, q over pi r squared, that was the density, the charge density of the disk. That's a big R, not a small r. Right? That the radius of the disk. The radius of the disk is big R, not small r. Whoopsies. Okay. Now we solve for dq. Just recopying it here so that dq is equal to q over pi r squared. Actually, why do we bother keeping I'm writing q over pi r squared? That's just sigma times 2 pi r dr. And we could cancel out a pi, but not much else cancels. So we can just write this as sigma 2 pi r dr, because sigma is a constant that we know. Okay, so that's dq. You could have left it in the other terms, but it doesn't matter. And now we're going to plug that into the integral in order to be able to do the integral. I just copied the integral from the other page. Now let's go ahead and plug in for dq. Remember the problem here is that we've got the variable r and the integral variable dq, so we had to relate them. That's what we're doing here, is we're now able to say we can integrate from r equals 0 to r equals r, k d dq, which is sigma 2 pi r dr, over r squared plus d squared to the 3 halves, and now we pull out all the so now we replace dq, and now we pull out all the constants, and once we put in dq, I just repeated myself, pull out all the constants, k, d, sigma, 2 pi, I think that's it, the integral, and now our integral variable is definitely little r, so little r goes from 0 to big R, and all we're left inside the integration is r dr over r squared plus d squared. Remember, d is a constant, but we can't pull it out because it's stuck in this denominator. And now we have to do this integral. And you say, okay, that's easy, right? Kidding, but it is an integral in a single variable. So how do you solve that integral? This is a really important question. If you're ever going to be an engineer or physics or go to grad school, whatever, you need to know how to solve integrals. This is a Calc 2 thing. You could do it. But honestly, the answer for a physics major is look it up. Look up the integral. And actually, it's even easier. You can just use an integral calculator online, like, for example, Wolfram Alpha, sorry. And you find that the result is... Actually, if you remember a little bit of Calc 2, let me just tell you, this is actually not a hard integral to solve because it is just substitution. You substitute, you say u equals r squared plus d squared, so that du is equal to 2r dr, and then you can go ahead and plug in, make this substitution for u and this substitution for r dr, and then it's an easy integral to do, and what you find is that the integral is that. Again, either look it up in an integral table, an online integral calculator, or just do it by substitution. It's actually quite an easy integral to do. And you find the result is that, and that we have not evaluated the limits yet, evaluated from the limits of 0 to r. So therefore, in the limits, you get this. You can actually simplify things by remembering that k is 1 over 4 pi epsilon 0. That just allows us to cancel some of the constants and just fixing up those minus signs, combining those minus signs. This is what you end up getting. This is the field due to a disk of radius r at a distance d above its center. Not showing that in this picture here. So the result of the field of disk, of a finite disk of radius r. Let's look at the side view here. At a distance d, at a point P, the field is in this direction, E disk, and all the up-down components cancel, all the x components add, and the field is what's circled in green. Now, what happens if we get off-center? What happens if we move to a point over here? Right? Now we're getting closer to one edge than the other, and it's more complicated because things aren't symmetric and it doesn't cancel, and the field, if we only move a little bit, it's probably still pretty close, but it starts to it starts to what's called fringing effects, right? As we get towards the sides, it's actually called fringe effects. As we get to the sides of the disk, if we stay near the center of the disk, we have approximately the same amount of field to the left and the right. I'm sorry, in this case, above and below. Then it stays pretty constant in the plus x direction. But when we get close to the edges, it starts to fringe. And I didn't do that calculation. It's a complicated calculation. But what we want to think about is, what if this disk is really big compared to D? In other words, what if R is really big compared to D? R is really big compared to D, or if R is infinite, if it's an infinitely large disk, an infinitely large sheet of charge is what we started talking about, we never get close to the edges and we don't get this fringing effect. And the field is relatively constant because we say there's always, if it's an infinitely large disk, there's always the same amount of charge to the left and to the right and to the above and below, so that all the components cancel except for the components pointing away from the disk. So we say, what if R is much, much greater than D? If R is much, much greater than D, look at this equation. Say if R is much, much greater than D, if D is small compared to R, so that we can just make R equal to, or we can just make R equal to infinity, an infinitely large disk, right? Let's just say that. We don't even have to say R is much, much larger than D. We can just say it's an infinitely large disk, R equals infinity, plug in R equals infinity. What happens? If we plug in R equals infinity, this term goes to 0, and all we're left with is d sigma over 2 epsilon naught times 1 over d. And so we're left with, for an infinitely large disk, it's sigma over 2 epsilon naught. It's a very simple equation. So E for an infinitely large disk, or a large sheet, right? So it doesn't even have to be a disk now. It's just an infinitely large sheet of charge, two-dimensional sheet of charge. Doesn't matter what shape it is because you can't see the edges. Is sigma over 2 epsilon naught. That is a particularly interesting result. It is a constant, right? It is not dependent on how far away you are from the sheet, right? It's not dependent on D. The D's canceled. The D's canceled. It doesn't depend how far away you are from the sheet. So this is what gives you a constant field. An infinitely large sheet of charge, and we are talking about positive. If it's negatives, the field is just going to be in the opposite direction. Instead of away, it's going to be towards the sheet. Gives you a constant field as long as we never get near the edges, right? Obviously getting near the edges, where E is sigma over 2 epsilon 0. Sigma, remember, is a constant. It's a constant. It's the charge density. It's the charge density. And epsilon 0 is just a constant. Remember, it comes from K. K equals 1 over 4 pi epsilon 0. Epsilon 0 is the permittivity of free space. And it's something like 8.99 10 to the minus. I don't know. I don't remember what it is. Look it up. But it's a constant. So this is an important result because it's going to be true when we're close to any charged object. If we're close, then it looks like a flat sheet. Just like, again, when you're close to the surface of the Earth, the gravitational field comes from the fact that it looks like it's a constant gravitational field. It looks like it's a flat Earth. It doesn't look round, it can't see the edges. And it does turn out to be a constant, right? So the electric field of a sheet of charge, an infinite sheet of charge, is sigma over 2 epsilon 0, where sigma is a constant and 2 is obviously a constant, epsilon 0 is a constant. Remember that sigma is just the charge per unit area, and this is assuming that it is uniformly charged, just like the Earth has a uniform gravitational field close to the surface of the Earth. The sheet is uniformly charged. Now we've left off here, we've sort of lost the fact that E is a vector, and remember that the electric field pointed away from the ring perpendicularly, therefore away from the disk perpendicularly, therefore away from the sheet perpendicularly. And so we're going to have to add the direction, and now it's not a radial direction, because radially means along a radius from a point. Now it's always pointing perpendicularly from the sheet at any point, as long as, again, you're not close to the edge of the sheet. It's going to look like it's perpendicularly from the sheet, and that's the normal direction. The n hat means normal direction. N hat is normal direction. We know what normal means. It's the perpendicular direction to the sheet. Now remember that charge comes in two flavors, plus and minus. And if you put a positive charge on a sheet, whether it's a conducting sheet, an insulating sheet, if you have a even charge, constant charge density across the sheet, and it's positive, then this is going to turn out to have a direction of positive n hat with a bunch of numbers in front of it. But if it's negative, the direction is going to be negative n hat. So for a sheet of positive charge, the electric field is always pointing away, and the lines are all parallel to each other. Remember, that means that it's constant. It doesn't get smaller as you get farther from the sheet. Now, in reality, when does it get smaller? It gets smaller when you get far enough away that you can see the edges. But we're assuming that you don't do that when we're talking about a sheet of charge. We're either talking about an infinite sheet or that you're close enough that you don't see the edges. So the field lines are all parallel to each other. Again, it doesn't get smaller as you get farther away, right? The Earth's gravitational field, until you get really far away, doesn't get any smaller. Acceleration due to gravity is approximately 9.8 meters per second squared, whether you're on the ground or whether you're at the top of a building. The Earth still looks flat. So the electric field, due to an infinite sheet of charge, is constant and doesn't get any smaller as you get farther away. So the electric field map is a bunch of parallel lines. That's what we talked about in class the other day. I showed you an electric field map of parallel lines and told you that that could only come from an infinite sheet of charge. Now, so what would a negative sheet look like? What would the field map of a negative sheet look like? The electric field must point towards the sheet, and again, on both sides, whether we're above it or below it, or to the left of it, to the right of it, the electric field lines point towards the sheet because a positive test charge would move towards the sheet. So an electric, never mind, scratch what I was about to say. So this electric field magnitude of sigma over 2 epsilon 0, that's the electric field on either side of the sheet. That's important, right? That the electric field on top is sigma over 2 epsilon 0. The electric field on the bottom has a magnitude of sigma over 2 epsilon 0. Same here, sigma has a magnitude of sigma over 2 epsilon 0. Top, bottom, whoops, I forgot the subscripts. Bottom, top equals sigma over 2 epsilon 0. So the electric field on both sides of sigma over 2 epsilon 0. So speaking of sheep, I guess we weren't speaking of sheep. We were speaking of sheet of charge. Anyway, speaking of sheep, what do you call a sheep with no legs? A cloud. I don't really care if that wasn't funny.